In this video, we'll discuss the chain rule to differentiate composite functions. Here are the main points to be addressed in the video. The chain rule is used to differentiate the composition of two or more functions. The derivative of composite of two functions, f and g, is not the composition of their derivatives. This equation provides a method for taking the derivative of a composite function, f of g. The method is called the chain rule for differentiation. It says that the rate of change of a composite function is a product of composed functions' rate of change. Let's take a look at a couple important features of the chain rule. F is the name of what is often called the outside function. And g of x is called the argument of the function f, and also often called inside function. When differentiating a composite function, you need to take the derivative of the outside function while keeping the argument g of x in this case. You then multiply f prime of g of x by the derivative of g with x as its argument. Now let's look at some examples. Sometimes the hardest part is determining whether you can use the chain rule. Here are 6 examples. Pause the video and decide for which of these functions you would need to use the chain rule to compute its derivative. In order to determine whether we can use the chain rule for each example, we need to identify the outer function and the argument, inside function. For h of x, it's probably not too difficult to figure out the outer function will be sine of x, and the argument will be 3x squared. Because if you replace the argument of f of x with g of x, you get sine of 3x squared. For q of t, it might be a little more difficult to see. But you can use f of t equals to e to t as your outside function, and g of t equals 1.44t as your argument. So q of t is a composite function, and you could use the chain rule to compute its derivative. For r of z, the logarithmic function might look unfamiliar, but you can use log base 3 of z as the outer function, and 4z minus 7 as the argument. M of w looks a lot like r of z. However, in this example, you're not composing two functions. Instead, you're taking product of 4w minus 7 and log base 3 of w. So you need to use the product rule rather than the chain rule to compute the derivative of m of w. For s of u, if you rewrite the square root as 1/2 power, then you can use u to the 1/2 power as the outside function and 4u minus 7 as the argument. Finally, for p of y, you could compute the derivative of each term separately. Alternatively, you could use 3y squared minus 7y plus y to the half power as an outside function and natural log of y as the argument. Now that we identified the functions for which we could use the chain rule to compute their derivative, let's look at h of x to find the derivative. For the first example, we have h of x equals sine of 3x squared. We want to write h as a composition of f and g. The outside function f is sine of x, and g, the argument, is 3x squared. The next step is to compute the derivative of outside function and argument. Here's the derivative of f is cosine of x, and derivative of g is 6x. To use the chain rule, we need to take the derivative of outside function, plug in the argument, and multiply by the derivative of the argument. So the derivative of sine is cosine. Then plug in the argument, and then multiply by the derivative of the argument. Now let's look at the second example. Let q be an exponential function in terms of t. We need to write q as composition of f of g of t. Here f, the outside function, is e to the t, and g, the argument, is 1.44 times t. Next, we need to find the derivative of outside function and the argument. The derivative of e to the t is e to the t, and derivative of 1.44t is just 1.44. Putting this together with a chain rule, we take the derivative of the outside function, plug in the argument, and then multiply by the derivative of the argument. Let's look at one more example. Let r be a log function in terms of x. We need to recognize that f is a composite function. Here f, the outside function, log base 3 of x, and g, the argument, is a linear function 4x minus 7. Next, we need to compute the derivatives of the outside function and the argument. Here, derivative of f is 1 over x times 1 over natural log 3, and derivative of g is just 4. To apply the chain rule to compute the derivative of r, we first have the derivative of the outside function. And I've left some extra space here because we'll plug in the argument in place of x. Then we'll multiply the derivative of the argument. So now we have stated the chain rule and have used it with 3 different composite functions. Now that you learn how to use the chain rule, I'll explain why the chain rule works. First, let's talk about the composite function. Here are the graphs of 2 functions, g of x and f of x. And we'll pick a value of x and call it a. Let's consider what it means to evaluate f of g of a. We begin by evaluating the function g at input x equals a, which yields the output value g of a. This value g of a is then used as an input to the function f, which yields output value of f of g of a. So if we think about the graph of composite function of f of g of a, if we used a as an input, then the function f would produce corresponding output value and would put this together to plot a coordinate on the graph. As this animation illustrates, composing functions involves taking the output of one function as the input to the another function. This concept will be important as we examine the chain rule. Next, let's quickly recap the meaning of a derivative. We often write the derivative of a function f of x at a point x equals a as f prime of a. We can think of this graphically in terms of slopes. From our values of a, we have an amount of change of x and a corresponding amount of change of f. And the ratio of delta f to delta x is the slope of this green secant line. However, since the graph is not a straight line, this slope is only an approximation of the value of the derivative. But we can get a better approximation if we use smaller values of delta x. As delta x got smaller, the graph of function f looked more and more like a straight line. When delta x is this small, we refer to delta f as df and delta x as dx. The value of the derivative of f evaluated at a is the slope of the tangent line is the ratio of df corresponding to dx. So over a really small change in x, the amount of change in f is f prime of a times as large as the amount of change in x. So we can label the length of the blue vertical arrow as f prime of a times as large as the length of the red arrow, dx. Now let's put this together, the idea of composing functions with the definition of derivative to understand why the chain rule works. On the left, we have a graph of function g, and on the right, we have the graph of the function f. We have already zoomed in a lot on these functions. Our goal is to understand the derivative of composite function y equals f of g of x. We know that the derivative of a function at a value x equals a is equal to the ratio of small change in f corresponding small change in x. So we want to know how much the output of composite function changes as input changes by the really small amount, dx. Let's mark off x equals to a on the graph of g of x. As x changes by a small amount from a, dx, since we've zoomed in far enough for the graph of g of x to look linear with the slope equals to g prime of a, the corresponding change in g is equal to g prime of a times dx. Next, let's think about the composite function of f of g. We need to think about output of g of x as an input of f. So now we'll think about the value of g of a as an input to the function f. Then the change in g becomes a change in input to the function f. The resulting change in output of function f is df. Since we have zoomed in, the slope of f appears essentially constant. So any small change in y is f prime of g of a times as large as the corresponding change in x times dg. Now, since dg is equal to g prime of a times dx, we can replace it. And we can write df as f prime of g of a times g prime of a times dx. Since dx is in both numerator and the denominator of this expression, we can cancel this amount, which shows that the derivative of composite function can be written as a product of the derivative of f evaluated at g and derivative of g evaluated at a. This gives us general chain rule for the differentiation. The derivative of a composite function f of g of x is equal to the derivative of f with the argument g of x multiplied by derivative of g.